Okay, in this video, let's take a look at the structure and functional properties of myoglobin. Now, before we get directly into myoglobin, let's recall the transport of oxygen in the body. We have oxygen that we breathe, which enters our lungs. The oxygen is transferred across the epithelial lining of the lungs, enters the blood, and enters red blood cells. In the red blood cells, the oxygen needs to bind to a carrier. This carrier protein is hemoglobin. The red blood cells travel around the bloodstream, transporting the oxygen bound to hemoglobin, and when the red blood cells encounter tissues that are in need of oxygen, this oxygen is transferred from hemoglobin into muscle. For example, muscle is a very high user of oxygen because of its need for energy. Now, the oxygen that's transferred from hemoglobin to muscle, some of it is used immediately, but most of it is actually stored. And it's stored bound to myoglobin. So myoglobin is the major storage binding protein of oxygen in muscle tissue. Now let's take a look at the structure of myoglobin. Myoglobin is a single polypeptide. It is a globular structure, which means that it has a lot of alpha helices that fold back on itself. And being a single polypeptide, it has the storage capacity for oxygen bound to what's called a prosthetic group. So the oxygen that binds to the molecule, the protein of myoglobin, is not actually binding to the protein itself. It's binding to a prosthetic group, which is called heme. The heme is a specific structure we'll take a look at in a second, and this is bound to the center of the myoglobin protein. Heme binds iron. And this particular iron is in a 2+ state. Recall that iron can be either in a 2+ reduced state or an oxidized 3+ state. In the 3+ state, it is ferric iron. In the 2+ state, it is ferrous. So it is actually the iron that is bound to the heme that is going to bind the oxygen. The myoglobin itself is just a structural component of protein that is able to bind the heme and coordinate the oxygen binding. So now let's take a look at the heme molecule itself. The heme molecule consists of 4 pyrrole rings. The pyrrole ring, recall, is this structure, and it has nitrogens coordinating its center structure. So we'll draw 4 pyrrole rings here, and then we will link these pyrrole rings together. Now there's various double bonds distributed, of course, in the pyrrole rings, and there are groups that come off of the pyrrole rings. And these are all involved in the biosynthesis of heme. But what I'd like you to recall is just the basic structure of heme itself with the 4 pyrrole rings. The importance of the pyrrole rings are the nitrogens on these rings face inward. These nitrogens then can be a coordinated binding site for iron in the center. Now this is the basic structure of heme, but in order to look at the functional properties of heme iron, we need to take this structure and turn it 90 degrees. So let's turn the Perol structure 90 degrees, and we will place our iron in the center here because of the nitrogens that are coordinating this interaction with iron to hold it in place. Now the primary interaction of heme with the protein myoglobin is going to occur through a histidine amino acid. This histidine is part of the polypeptide of myoglobin, and it is binding the heme to the protein. For example, here is our side chain of histidine, and notice that the nitrogen is now able to bind to the iron because the iron is in a 2+ state. So in addition to the nitrogens on the Perol rings binding and coordinating the binding of iron into the heme structure, this iron is also bound covalently to a histidine residue in the polypeptide backbone of myoglobin. So this is how the heme is anchored within the structure of myoglobin. Now what we have here is an opportunity for oxygen to form the final and sixth bound substance to iron. So we have 4 binding sites in the Perol rings. We have a 5th binding site with the histidine side chain. And now the 6th binding site on iron can be occupied by oxygen. In this structure, the oxygen is very stable, bound to the myoglobin structure. Now the stable binding, what this really means is high affinity. Now high affinity binding of oxygen to myoglobin makes sense because we want to make sure that our myoglobin is fully saturated as much as possible with oxygen so that our muscle tissues are not deprived of oxygen. So in order for this to be true, we need to have our myoglobin have very high affinity for oxygen binding. So recall our kinetics. If we say our ligand equals, in this case, oxygen, if our protein equals myoglobin, the kinetics of this reaction is going to be oxygen plus myoglobin to form the oxygen myoglobin complex. So here's their substrates in our reaction, here's our product we're forming. Now of course there are rates of association, K1, rates of dissociation, K2. Now recall that the Ka, which equals the association constant, is equal to the product of our complex formation of oxygen and myoglobin over our substrates, the concentration of oxygen times the concentration of myoglobin. This is our association kinetics. This, of course, equals the association rate over the dissociation rate. So high affinity binding, if we apply this equation, indicates that we have a large amount of oxygen myoglobin complex formed relative to the concentration of oxygen in myoglobin. So this means that the reaction is being driven to the right. So high affinity means greater product formation, which equals a very high association constant. Now if we look at this in terms of Kd, which recall is our dissociation constant, the dissociation constant, of course, is the reverse reaction. So this is the concentration of our products of the reverse reaction, which is free oxygen and unbound myoglobin, over the concentration of our complex, our myoglobin oxygen-bound complex. If we look at the rate kinetics, this is the dissociation rate over the association rate. Now this is essentially the inverse of Ka. So this is equivalent to 1 over the association constant. So in terms of Kd, when we're discussing affinity, what we want to see here is very little product form in the reverse reaction and a high concentration maintaining in the complex form. So this means that high affinity for Kd equals a very low dissociation constant.